Welcome to Module 4 of Chapter 7. In this module, we cover concepts like covering number of a graph, that is vertex covering number of a graph, edge covering number of a graph, independent sets, and matching of a graph. A set of vertices are said to be independent set if no two vertices of it are adjacent. A set of edges is said to be matching of a graph if no two edges in that set are adjacent. In module 4 is about matching and covering of a graph. The objectives of this module are independence number of a graph, matching and perfect matching and matching number, edge and vertex cover and covering number of a graph. First we define what are independent sets. A set of vertices, say S, in a graph is called an independent set if no two vertices in S are adjacent. A graph may have independent sets of different sizes. The independent set with maximum number of elements is called maximal independent set. That is, if we add any vertex to this set, it will no longer be an independent set. A graph may have maximal independent sets of different sizes. The number of elements in the largest maximal independent set is called independence number, denoted alpha naught of x. We now will illustrate with an example. We are going to find out independent sets in a Petersen graph. Recall that chromatic number of a Petersen graph is 3 and it is a graph on 10 vertices. Hence, there exist set of 4 vertices which have been colored with same color. Hence, its independence number is 4. Using coloring of a Petersen graph, which is given below, we will illustrate now. We see that the independent sets are C1, C8 and C9. C1, C8 and C9 have same color. C2, C4 and C10 have same color. C3, C5, C6 and C7 also have same color. So, there are all these 3 sets are independent, but there is a independent set with 4 vertices. So, we cannot have more than this. So, independence number of Petersen graph is 4. Now, we will see few properties of this independence number. Since independence number, the independent set, all the vertices independent set with this can be assigned with the same color. So, it is independence number and chromatic number of a graphs are related. So, following result shows that one. Let x be a simple graph on n vertices, then n by chromatic number of complement of the graph x less than or equal to n by alpha naught of x, which is less than or equal to chromatic number of x, which is less than or equal to n minus alpha naught of x plus 1. Proof: let chromatic number of x equal to k, then V of x can be partitioned into k sets V1, V2 and so on Vk, such that all the vertices in Vi for 1 less than or equal to I less than or equal to k are colored with the same color. Consequently, each of the sets V1, V2 and so on Vk are independent sets. Let Ni is the cardinality of Vi for 1 less than or equal to I less than or equal to k, then Ni is less than or equal to alpha naught of x. Since alpha naught of x is the independence number, it is the cardinality of the maximal independent set, and all these are independent sets. V1, V2, Vk are independent sets. So, clearly Ni is less than or equal to alpha naught of x for 1 less than or equal to I less than or equal to k. Hence, n is equal to summation I is equal to 1 to k Ni less than or equal to k times alpha naught of x. Thus, we will get n by alpha naught of x is less than or equal to chromatic number of x. Let S be a maximal independent set. Then S contains alpha naught of x vertices. as chromatic number of graph is chi of x, and we can color all the vertices in S with the same color. So, we can see that chromatic number of x minus S, if you delete S vertices from X, that x minus S, chromatic number of that graph is greater than or equal to chromatic number of x minus 1, as x minus S has n minus alpha naught of x vertices. So, chromatic number of x minus S is less than or equal to n minus alpha naught of x. Thus, chromatic number of x is less than or equal to chromatic number of x minus S plus 1, which is less than or equal to alpha minus n minus alpha naught of x plus 1. Finally, we note that x complement contains a subgraph having complete graph on alpha naught of x vertices. Hence, chromatic number of x complement is greater than or equal to alpha naught of x, or n by chromatic number of x complement is less than or equal to n by alpha naught of x. That is the required result. Now, another result says that let x be a simple connected graph on n vertices, then 2 times root n is less than or equal to chromatic number of x plus chromatic number of x complement, which is less than or equal to n plus 1, and n is less than or equal to chromatic number of x into chromatic number of x complement, which is less than or equal to n plus 1 by 2 whole square. It is known that chromatic number of x into chromatic number of x complement is greater than or equal to n. We also know that arithmetic mean is greater than or equal to the geometric mean. Hence, one has chromatic number of x plus chromatic number of x complement by 2 is greater than or equal to square root of chromatic number of x into chromatic number of x complement. Thus, we also get chromatic number of x plus chromatic number of x complement is greater than or equal to 2 times root n. Now, it is sufficient to show that chromatic number of x plus chromatic number of x complement is less than or equal to n plus 1. This can be shown by induction on n vertices. Induction on n is the number of vertices. This is leave it as an exercise. Also, another exercise is nice to find independence number of kn, kmn, cn, wn and any tree on n vertices. Let x be a bipartite graph. A graph x is bipartite graph if and only if every subgraph y of x there is an independent set containing at least half of the vertices of y. Every bipartite graph has a vertex partition into 2 independent sets, one of which must contain at least half of the vertices, though it need not be the maximal independent set. Since every subgraph of a bipartite graph is bipartite, the argument applies to all subgraphs of bipartite graph as well. Hence, the condition is necessary. For the converse, suppose x is not bipartite. By characterization of bipartite graphs, x contains an odd cycle, say y. This subgraph y has no independent set containing at least half of the vertices, as every set containing at least half of the vertices is in an odd cycle must have 2 consecutive vertices on the cycle. Thus, we arrive at a contradiction, hence the result follows. Matching of a number. Let x be a simple graph, then a matching in a graph x is a set of edges which do not share any endpoints. The vertices incident to the edges of a matching, say M, is said to be saturated by M. A perfect matching in X is a matching that saturates every vertex. The problem, find all perfect matchings in Knn. So, we will illustrate with first with K44. The following are few matchings in K44. K44 contains 8 vertices x1, x2, x3, x4, y1, y2, y3, y4. So, one perfect matching is x1 to y1, x2 to y2, x3 to y3 and so on. Another perfect matching is x1 map to y2 and x2 map to y1, x3 map to y4 and x4 maps to y3, and like similarly other two also they are also matchings in K44. So, now we can see that matching is nothing but mapping from x1, x2, x3, x4 to y1, y2, y3, y4, which is both 1, and onto mapping. So, number of perfect matchings is equal to the number of 1, onto mappings from the set x1, x2, x3, x4 to y1, y2, y3, y4. So, in general, if let vertex set of Knn is partitioned like this x1, x2 and so on xn, y1, y2 and so on yn, then the matchings in the above example one can easily show that there are n factorial perfect matchings in Knn, one for each permutation of 1, 2, 3 and so on n. So, now we are going to find out number of perfect matchings in a complete graph K2n. Let Fn be the number of perfect matchings in K2n, then it can be easily observed that Fn satisfying the following recurrence relation. Fn is equal to 2n minus 1 into Fn minus 1, where F0 equal to 1. If you simplify this, we will get Fn is equal to 2n factorial by 2 power n into n factorial. This can be proved in some other ways also, but here we proved by using recurrence relation. Now, we are going to define maximal and maximum matching. Let X be a simple graph, then a maximal matching in X is a matching say M such that for every edge E in edge set of X minus M, the set M union E is not a matching. That means, if you add one more edge to the matching set M, then it is no longer a matching, then it is called a maximal matching. A maximum matching is a matching of maximum size among all the matchings in the graph. This is called maximum matching. Every maximum matching is a maximal matching, but converse need not hold. One can check with the path graphs P4 and P5. Now, we will illustrate an example to show what is a matching, what is a maximal matching and so on. If you look at this graph has 10 vertices. Note that the graph given above, the sets M1 contains the edge 1, 5, edge 2, 6, edge 3, 4 and edge 7, 8. So, 1, 5, 2, 6, 3, 4 and 7, 8. So, none of these edges are adjacent, there is no common end point. So, M1 is a matching. Similarly, M2 is also a matching 1, 5, 2, 6, 3, 4 and 7, 9. So, say instead of 7, 8 we can take 7, 9. Similarly, M3 same 1, 5, 2, 6, 3, 4 but 7, 10 and M4 is 1, 5, 2, 6 and 3, 4 only, and M5 is 1, 6, 2, 3 and 4, 7. So, they are all matchings. Among them M1 is a maximum matching, whereas M5 is maximal. One can see that we cannot add one more edge to M5, 1, 6, 2, 3 and 4, 7. If we add any more edge, then it is no longer a matching. So, M5 is maximal matching, but it is not a maximum matching. So, we have a maximum matchings, means matchings with larger than the cardinality of M5. Also note that M4 is not a maximal matching, hence it cannot be maximum matching as well. For M4 it is still possible to add one more edge. So, it is not a maximal as well as maximum matching. Every perfect matching is maximum matching, but converse is not true. Now we will define an M alternating path. Let X be a simple graph with a matching M, then an M alternating path is a path that alternates between edges in M and not edges in M. An M alternating path whose endpoints are unsaturated by M is called an M augmenting path. In the graph given below, M is equal to 1, 2, 5, 9, 6, 10, 3, 4, 8, 11 is matching with 5 thin edges. So, the diagram is given below. So, and M dash equal to 1, 5, 2, 6, 9, 10, 3, 4, 7, 8, 11, 12 is the matching with 6 bold edges, and the red edges belongs to neither M or M dash. The two matchings have common edge 3, 4. So, it is not in the symmetric difference of M and M dash. The edges in the symmetric difference M and M dash form a cycle of length 6 and a path 3. So, it is easy to see that M symmetric difference M dash is the cycle 1, 2, 5, 10, 9 and 5, and also the path of length 3, that is 7, 11 and 12. So, that previous example motivates for this lemma. Every component of a symmetric difference of two matchings is a path or a even cycle. Let M and M dash be matchings, and let F is equal to symmetric difference of M and M dash. Since M and M dash are matchings, every vertex has at most one incident edge in each of them. Thus, the graph F has at most 2 edges at each vertex. So, delta of F is less than or equal to 2. Thus, every component of F is a path or a cycle. Furthermore, every path or cycle in F alternate between the edges of M minus M dash and M dash minus M. Thus, each cycle has even length with equal number of edges from M and M dash. Hence, the result follows. Now, we are going to give Berge theorem. It is derived in 1957. The matching M in a graph X is maximum matching if and only if X has no augmenting path. We prove the contrapositive in each direction. That is, we prove that X has a matching larger than M if and only if X has an augmenting path. Let V0, V1, V2 and so on V2k, V2k plus 1 be an M augmenting path, then by definition V2i minus 1 comma V2i belongs to M for 1 less than or equal to I less than or equal to k. So, we see that the matching M dash V0, V1 and so on V2k, V2k plus 1 is larger than M. For the converse, let M dash be a matching in X that is larger than M. We now construct an M augmenting path. Let F is equal to M symmetric difference M dash. Then by previous lemma, F consists of a paths and even cycles with the condition that the cycles have same number of edges from M as well as M dash. Since cardinality of M dash is greater than cardinality of M, F must have a component with more edges of M dash than that of M. Hence, this component can only be a path that starts and ends with edges of M dash. Thus, this path is an M augmenting path in X. Now, we are going to give another result, that is, if number of vertices in the graph is equal to 2n and the minimum degree of the graph is greater than or equal to n, then x has a perfect matching. If the graph x has 2n vertices, each of degree greater than or equal to n, then the graph has a perfect matching. The proof: we assume that we have been given the set say S consisting of r less than n pairs of vertices such that the elements in S are already paired off. The proof gives an algorithm to increase this pairing to r plus 1 pairs. If there are two vertices which have not yet paired off and are joined by an edge, then this pair can be included in the set S to get required set containing r plus 1 pairs. So, let us assume that none of the remaining vertices joined by an edge. Now, choose any two of the remaining vertices, say A and B. We will now show that there must exist U and V belongs to S which are already paired off, but they have a property that the AU and BV are edges in the graph X. Thus, in this case the pairings can be rearranged so that A is paired with U and B is paired with V, hence increasing the number of pairs to r plus 1. So, in the contrary, assume that such a pair does not exist, then each of the pairs x comma y belongs to S is such that among the possible edges Ax, Ay, Bx, By and By, either Ax, Ay or Bx, By or Ax, Bx or Ay, By actually appear in the graph. Thus, total number of edges from r pairs of vertices in S to A and B is at most 2r, which is less than 2n. But since degree of A and degree of B is greater than or equal to n, the total number of edges from S to A and B must be greater than or equal to 2n, gives a contradiction. Thus, the result follows. The above proof can be seen as an algorithm. Having obtained R pairs, scan the remaining 2n minus 2 vertices to look for adjacent vertices. If not, choose any two of them, say AB. We can scan the pairs x and y already formed until a pair is found such that A is joined to x and B is joined to y. Then replace the pair xy by the pairs Ax and By. So, if r plus 1 is less than n, then repeat the whole process. We covered the concept maximum matching, maximal matching and perfect matching. We also proved a result which relates maximum matching with m augmenting path. Now, we are going to define and prove various properties of vertex covering of a graph and edge covering of a graph. Now, we define the concept edge covering and vertex covering. First, we start with edge covering. In a graph X is equal to V comma E, the set C contained in E is said to be an edge covering of X if every vertex in X is incident with at least one edge in C. The set of edges that cover a graph is called an edge covering or covering subgraph or simply covering of X. Covering exists if and only if graph has no isolated vertices. That is easy to see. A graph that has no isolated vertex is trivially its own covering. Means if you take all the edges, then it is clearly a covering. The set of edges in the spanning tree of a connected graph is also a covering. So, these are illustrating what is a edge covering means. The set of edges in Hamiltonian circuit, if one exists in a graph, is also a covering. Now, we are defining what is a minimal covering. A covering from which no edge can be removed without destroying its ability to cover the graph. Every covering contains a minimal covering. Minimal covering of n vertex graph will have at least n by 2 floor of n by 2 edges. It is because each edge covers 2 vertices, so we need to have that many edges. Every pendant edge in the graph has to be included in every covering of the graph. No minimal covering contains a circuit, for we can always remove an edge from the circuit without leaving any of the vertices in the circuits uncovered. Therefore, minimal covering of n vertex graph can contain no more than n minus 1 edges. A graph in general may have many minimal coverings and they may be of different sizes. The number of edges in the minimal covering is the smallest size, that has the smallest size is called edge covering number of the graph. Similarly, we can define vertex covering of a graph. We simply use the word covering for both vertex covering and edge covering. It should be clear from the context. So, a vertex covering of a graph is a subset of vertices S such that each edge of the graph is incident with at least one element of S. One can define minimal vertex covering in the same way as minimal edge covering. A graph in general may have many minimal vertex coverings and they may be of different sizes. The number of vertices in a minimal vertex covering of that smallest size is called vertex covering number of the graph. So, now we are going to prove an important result given by Koenig and Avery theorem. The theorem states that let x equal to v comma e be a simple connected graph, then S contained in V is a vertex cover if and only if V minus S is an independent set. So, here we are relating vertex cover of the graph to independent set. Now, we see the proof of this theorem. If S is an independent set, then every edge incident to at least one vertex of V minus S. Conversely, if V minus S covers all the edges, then there is no edge that is joins the vertices of S. Now, another theorem, it is given by Koenig and Avery in 1931. In any bipartite graph, the number of edges in a maximum matching is equal to the number of vertices in minimum vertex cover. We covered vertex covering of a graph, edge covering of a graph, and vertex covering number and edge covering number of the graph. With this, we end this module.